Hi, today we're gonna discuss why bifurcations are more common on the circulatory system instead of trifurcations. First, we're gonna talk about the principle of minimum work that was proposed by Murray in the 1920s. And this law on the harmonization of the vascular dimension explains that to minimize the total energy caused by balancing energy lost to the shear stress and the energy required to sustain the total blood volume through the vascular tree. To make this principle, Murray made several assumptions, such as that the blood flow is not pulsated, has a parabolic laminar flow profile and exerts constant shear stress on the arterial wall through the vascular tree. Also, that the vessel is straight and rigid. And the last one, that the flow is described by partial equation for flowing tubes. The implication is that almost the 94% of the frictional losses can be saved by doubling the radius of the tube while keeping length and other variables constant. Other researchers, such as Rossetti and Lofgren, proposed that the vascular dimensions of the cerebral arteries follow the principle of minimum work, and that the bifurcations of the cerebral arteries appear to be optimized to avoid increased hemodynamic stress. While the principle of minimum work may apply at the intracranial portion of the carotid artery, its applicability at the extracranial carotid artery bifurcation has not been tested yet.
We're going to check some of the studies that have been made regarding arterial design and its evolution. First, in 1515, Leonardo da Vinci described three bars as preserving cross-sectional area at branches. Then in 1708, Keel made anatomical measurements of arteries from dog, calf, and man with the aim of calculating the quantity of blood in the human body. In 1708, Wahlberg provided a detailed description of Keel's work on the arterial network and his relationship to the English iatromechanists. In 1808, Young referred to Keel's data in his 1808 Cronion lecture, where he assumed a consistent increase in area of 1 to 1.26 at each arterial bifurcation. Then in 1878, Rocks, in his doctoral thesis later in the 19th century, undertook a detailed study of the relationship between diameters and the angles obtained by arteries at bifurcations. He concluded that the shape and direction of the lumen of the blood vessels at their branch point is mainly determined by the action of hydrodynamic forces. In 1901, Richard Thomas proposed that the size of the arteries depended on the velocity of the blood flow in the vessel. He proposed that the diameters between parent and offspring branches conform to an exponential relationship, as we can see in the equation, where R0, R1, and R2 are the radial of the parent and offspring branches at a bifurcation, and X is the branching exponent, also termed the bifurcation or junction exponent. Then in 1903, Hess extended Rock's work on branching and suggested that a typical branching angle of around 70 degrees could be explained by minimization of energy losses, stating that the most favorable branch angle is the angle whose cosine is equal to the ratio of the energy loss the blood undergoes in the parent vessel compared to a branch of the same length. Then we got Thomson, who referred in 1917 to both Rock's and Hess's work and reproduced Hess diagrams and calculations in the first edition of his classic work on growth and form, published in the same year. A few years later, Murray in 1926 published three articles which are known ultimately as the most influential studies of this era, and those are now widely viewed as the seminal early works on optimally principles in vascular design, and gave rise to the eponymous Murray's law. In the first pair of papers, Murray aimed to find physical laws that describe the organization of the vascular system in relation to oxygen transport and exchange at the capillary level. He envisaged this as a problem of maxima and minima, and employed the idea of two competing economic factors, the cost of blood flow and the cost of the blood volume, using an assumption of Poisson flow that the cost of the blood volume per unit length was proportional to the area of the vessel. Murray calculated that for the maximal efficiency in terms of blood flow and volume, blood flow should be proportional to the cube of the radius of the vessel, or hence for a bifurcating network, minimization of cost would be achieved as we can see in the first equation. In a third paper, Murray extended his analysis to look at the angles subtended by branches with respect to the axis of the parent. Using the optimality arguments developed in his earlier paper, he calculated that the optimal angles subtended by the major and minor branches should theta 1 and theta 2 respectively, as we can see in the second equation, or for the combination of these angles, theta 1 plus theta 2, minus the branching angle as we can see in the third equation. Murray commented that Hess had neglected the conditions in the other branch or continuing segment of the parent artery on his analysis, and that his conclusion was therefore incorrect. In 1954, Korn argued that four factors should be optimized: the size of the aorta, capillary dimensions and the volume of tissue supplied by a capillary, the connecting system between the aorta and the capillaries, and the total resistance of the system to flow. Then Taylor developed Korn's argument and applied them to pulsatile flow and elastic arteries, and he accepted the assumptions of minimum energy expenditure in terms of blood flow and blood volume, but also argued that it would be too costly in terms of cardiac work to allow the small arterial terminations to be impedance matched to the proximal conducting elastic arteries. Hence, reflections were inevitable. Samir then recognized that the optimality approaches outlined above lacked any plausible mechanism by which global optimality could be implemented. In 1981, Sherman published an influential review that summarized much of the work up to that time and examined the extent to which Murray's law fitted experimental data. He concluded that the fit was good, although not perfect, and he made some important points. First, the Murray's law might apply to an animate system if a trade-off between power and volume were made at some point during construction or development. Second, Murray's law would only apply to systems where flow conductance was proportional to R elevated to the 4. And third, changes in diameter would have to be coordinated across a large region. After those studies, West dealt with large arteries in an important but controversial paper on allometric scaling. Then Savage used a broadly similar approach to estimate that the transition from x equal to 2 to x equal to 3 might be expected to occur over arteries with diameters between 1 cm and 0.1 cm. Finally, but not less important, Huo and Kasab formulated a scaling law for vascular trees that related cumulative vessel volume, length, and diameter in an arterial trees. Consider the arterial trees as composed of multiple stem crown units and extended capillaries, since they were not considered tree-like structures.
With all that being said, there's still the first question. Why bifurcations instead of trifurcations? Well, according to Tahasashi and the experiments of simulations on pipes, we can extrapolate that the chamber before the split is where a power loss factor can be appreciated, and it only increases with the number of divisions. Therefore, there's more power loss in a trifurcation than the bifurcation. This means that in an optimal model, to satisfy the principle of minimum work, we should use bifurcations, as does the body.
Thanks for watching.